So thank you to be with us today. I am Pierre-Emmanuel Danet, the Technical Support Manager for ClimaLife. And I have the pleasure to be with Neil Roberts, who is our Senior Technical Sales Manager from Bristol in UK, and Gaël Maria, who is our Synergy Product Manager from Lyon in France. We will briefly remind you of the regulatory situation, summary. We will speak about difference between food safe and non-harmful products. Is it possible to reconcile a non-direct system with an economic interest? Quickly look on at the panorama of HTF, the interest of green renewables, and customers' testimonial. So I let Neil to start for the next slide.
Thank you, Pierre-Emmanuel. So we know the regulation situation with F-gas means that there are certain bans on higher GWP refrigerants, as well as a phase down in terms of carbon dioxide equivalents of the quantity of these products you can put on the market. The regulation situation encourages leak tightness in systems. Installations, therefore, like indirect chiller systems, enable more compact systems with reduced refrigerant charge and therefore considerably lower refrigerant leakage. Hence the interest in leak transfer fluids. Ooh. Oh, you've got it. We all know that refrigerants are subject to national and international regulations. But there are also a few things to know about heat transfer fluids. First of all, we are often asked, is there a food heat transfer fluid? It's important to understand that apart from water, it does not exist. Even ice water as a coolant cannot be considered in food in terms of food from the texts which govern the food industry. It is very important to not confuse non-harmful product with a food product. A food product is a product which is intended to be consumed. So you can understand why this is not a function of a heat transfer product, which is by definition not a food product. Nevertheless, we have the possibility to use heat transfer fluids in the food industry, where they have an NSF registration, which has two categories. HT1 is for where there may be food contact, and HT2 where there is no contact with food. NSF registration is an American classification which categorizes products according to their harmfulness. Therefore, an NSF HT1 heat transfer fluid can be used in the food industry where there is a possibility of incidental contact with food products during the processing, manufacturing, and packaging. So basically any situation except where you're deliberately adding it to the food product itself. This does not mean contaminated product is edible or marketable if a spill is detected, but equally, if the product is distributed and consumed before the leak is discovered, there is no serious health risk to consumers. On the other hand, a heat transfer fluid which is not NSF HT1 registered, but only NSF HT2, will make the product unfit for consumption, with all the consequences that entails. With this explained, let's look at how we can combine economy and efficiency with an indirect system. Firstly, why does an indirect system seem less interesting? Very simply, for design reasons. If we look at a direct system, it's basically a compressor, an evaporator, and a condenser. If we look at an indirect system, it's a compressor, an exchanger between the refrigerant and the heat transfer fluid, a condenser, and also a pump to circulate the heat transfer fluid in the system. Therefore, more energy is needed to compensate for the losses during the heat transfer in the refrigerant to heat transfer fluid exchanger, and the power to the electric motor of the pump. On average, 2% more consumption of each additional degree in evaporating temperature is used in an indirect application compared to a direct system. So to explain this a little further, if you have a system which needs a temperature of 0 degrees C, For a direct expansion system, it would typically operate at -5 evaporating temperature. For an indirect system, the evaporating temperature of the refrigeration system will be lower. If you require 0 degrees, the outlet of the heat transfer fluid heat exchanger will need to be -5. The inlet will need to be -10. And therefore, the evaporating temperature of the refrigeration system would need to be -15, i.e. 10 degrees lower than a direct system. So if you multiply that by the 2%, you can easily reach energy efficiency lower by 20% or more. So why opt for an indirect system anyway? The first advantage of a chiller is its more compact refrigeration system, which occupies less space, and it has a lower refrigerant charge. An indirect system is in a remote machinery room will allow the use of toxic, non-toxic, flammable or non-flammable fluids more easily than in a direct expansion system, thanks to the lower charge requirement, with easier compliance and safety constraints. What other ways are there to optimize energy consumption? First of all, we can look at the schedule of operation and optimize that, providing storage facilities that would be charged by operating machines during off-peak hours as much as possible. Do everything possible to have a correctly sized and well-controlled distributed network. And a fundamental point to choose heat transfer fluids which are suitable for the application. This is really important. The idea is have the lowest viscosity with the best thermal capacities at the desired temperature levels. Therefore, when choosing heat transfer fluids, certain characteristics must be considered. From a safety point of view, flammability, toxicity, and then you have to make sure you have compatibility with the application. Also, you need to make sure that the product you're using is suitable for use where when you're disposing of the product, you cannot just put it on the ground or for destruction. From a technical point of view, they meet a number of requirements. Anti-corrosion, material compatibility is really important. Chemical stability, surface tension, inhibitors, really important again. They have an impact on energy transfer, makes the system easier to control, and no biological action in the system. Protection of metals and high surface tension, good for wetting. These all help to improve the energy efficiency of the system. So what can we use? I'll hand over to Gail now to go through the range.
Thank you, Neil. Hi, everyone. So, as understood, selecting the proper secondary fluid or heat transfer fluid is actually major when you aim at efficiency or energy efficiency. And if you look at the range, we know that there are several and many bases available on the market. The ideal heat transfer fluid would actually be water. But as we know, water freezes at 0 degrees Celsius. It's not such of a help. Then there are some saline solutions that exist, such as temper products, which are proved to be very efficient, but can lead to several damages in case of leakage due to a high corrosion. Then there are glycols, solutions that we use for many, many years now, which are mostly, until now, non-renewable sources from petroleum sources, would I say. We have low-pressure organic fluids, such as R1233ZD, for example. And finally, we have a new generation of heat transfer fluid, which are biosourced or bio-based, so coming from vegetables from biosource, which are fully renewable, and which are the topic of today's presentation. So on this slide, you can see the operating ranges of those products. So when we look more specifically at a biosource product, what is it? Well, of course, first we grow what needs to be grown. And some specialists that have developed some specific bacteria to actually work and to create some fermentation. So those bacteria are, of course, deactivated. Their only purpose is to be able to transform the harvest to sugar, and then to the molecule we are looking for. So in this case, it will be 1.3 propanediol. And after fermentation, there is the refining protocol, which leads to the compound that we are looking for. So why are we looking at this? Of course, the environment is at the heart of our strategy. The idea is to have a lower environmental impact. And if we purely look at the life cycle analysis of the production of such molecules, you can see that the environment footprint of the greenware or the 1.3 biosource product is reduced by 40% when you compare it to a traditional MPG. By traditional, I mean which is not biosourced, of course. It is also 42% compared to a synthesis 1.3 propanediol, so compared to the same molecule, but which is a petrol-based one. So looking for a reduction of energy consumption and a lower environmental impact is obviously beneficial for us and for the planet and for the future. We've been looking at it's the main component of the greenware NEON, but of course, to make a heat transfer fluid, you also need some, I would say, more additives, such as inhibitors, in order to reduce and minimize as much as possible the corrosion. We aim to create a formula which is bacteriostatic, so of course to prevent the development of bacteria, fungi, algae in the system, and to create a product which is biodegradable, of course. Yeah, that's it. So now I'm going to hand over the mic to Pierre-Emmanuel Danet. No? Yes, I have to. Of course, because... Sorry. So we can look at some applications where we can find those heat transfer fluids. We could actually place them wherever an MPG is, even an MEG-based product, but we can find them and implement them in refrigeration, air conditioning, solar panels, hot water production, heat pumps, and so on. And it has its place in all industries, including, of course, food processing. As my colleague introduced the NSF registration. And I think it's the good transition now.
Thank you, Gail. So now we will speak about the characteristic of the product. As Neil said before, it is an NSF HT1 product, so it is really interesting for agro-food industry. But that's not the only one element in favor of greenware NEO. We have also other things to see to compare different HTF. The first benefits of greenware is its viscosity. As you can see, the viscosity is the same of MPG at -20, but when we come under -20, we have a really big difference between the two products. If we compare the viscosity at -10, we can see that we have a difference around 16 centistock, and at -20, we have a difference around 45% between the two products. So, of course, the consumption from the pump will be lower than with MPG base. If we look in the system, we compare two products at the same temperature protection, it's okay. We compare the product at -13, so -10 temperature in the system. And if we work with greenware NEO, we can win 3% or 7% regarding the constant flow against MPG solution. So for the same protection, we can gain 3 or 7% with the Greenway Neo base. And if we change the flow of the pump, we can increase the gain from 3 to 8% and from 7 to 12% just by reduce the flow of 2%. So, as you can see, we can make some reduce of consumption. We can have benefits with these products, and the production is better with the Green Neo than MPG base for the same cooling protection. So I think that it's to you, Gaël, no, to finish. No, it's not me.
Yes, it's you. Mais si, c'est marqué toi.
No. Non, c'est les customers testimonials, tu vas le faire mieux que moi.
Arrêtez de battre. So, here are some customers' testimonial of the project in action, actually. So we've been taking some agro-food examples where the Greenway Neo actually runs in the system. All those testimonials are also available to check on our website. So we invite you to also subscribe to our newsletter and to follow us on LinkedIn, as we share lots of these examples of the project in action. Actually, the main common point between the three cases, besides from having Greenway running in the system, is that we've been seeing major energy savings in all applications. It even helped getting a compliance to ISO 14001 and 50001 standards for French factory in France. And all data, if you want to look at numbers, all data are fully available on those cases. So yes, you can check them on our ClimaLife website. Thank you.